Hi, my name is Rishi Pathik, and this is my presentation for Lab 3. It is titled Determining the Mass of a Black Hole Through Observation of a Star Near It. So first, a quick introduction to the premise of my lab. The purpose of the lab was to estimate the mass of a black hole through the position-time data of a nearby star that orbited it. This is a fairly important concept as it is impossible to measure the weight for faraway objects or massive objects by simply weighing them. Instead, we have to observe their interactions with other objects near their system. The fundamental principles involved in this lab were Newton's law of gravitation, Newton's second law, and the idea of independence in orthogonal motion. This simply means that motion can be broken down and analyzed in perpendicular components. Now, let's examine the experimental setup. The quote-unquote experimental data that we were given was actually generated by a computer model and was meant to be analogous to the position-time data we might obtain by observing a body through a telescope. The star, which was our system, had a mass of 2 times 10 to the 30th kg and had only the gravitational force of the black hole acting upon it. The initial position and time that was set as time equals 0, and the initial velocity was calculated by measuring the change in position over the initial 24-hour period. The black hole, on the other hand, had its position fixed at the origin. Here's a graphical representation of the position data. The points represent the position of the star at different values of time. The model was developed with respect to the initial experimental data. The mass of the star was set to be 2 times 10 to the 30th kg, and the time between observations was set to be 86,400 seconds, or in other words, 24 hours. By looping through the position data, the initial and final velocities at each point were determined. From here, another loop was set up to determine the force acting upon the star. After finding the initial and final velocities, the change in momentum was determined. This value was set to be the net force acting on the object. It's important to note that while the quantities of net force and change in momentum are equal, they're actually slightly different. The net force is a quantity that cannot be intrinsically determined by observing. However, the change in an object's velocity or a change in an object's momentum can be observed, and it is pure coincidence of nature that these quantities are equal. After determining the net force, the black hole's mass was determined by rearranging Newton's law of gravitation and plugging in. Finally, the perpendicular and parallel components with respect to the star's motion of the black hole were found. The force parallel was found by observing the change in magnitude of the momentum. Again, this illustrates the important concept that a force cannot be observed, but rather has to be measured by observing the change in momentum. Finally, the perpendicular component of the force was calculated by subtracting the parallel component from the net force. Here's the model as it runs. We now investigate what would happen if the black hole's mass was changed or if the black hole was itself replaced by another black hole. By noting that the force of gravity equals the force felt in the perpendicular direction plus the force felt in the parallel direction, we can see that a change in the black hole's mass would change the star's orbit. For example, if the mass was increased, then the instantaneous speed of the star would also have to increase, or in other words, the orbital radius of the star would have to decrease. And this would be accompanied by a faster tangential acceleration of the star. The opposite would occur if the mass of the black hole was decreased. Now finally, a quick discussion of the results. The calculations of the masses of the black hole by the model varied at each time interval. These are shown in the graph above. The variations were small, but occurred because the position-time data wasn't smooth, as it was recorded in 24-hour time intervals. This forced a less accurate calculation of the object's velocity, which in turn caused the determined net force that would suddenly jump at each time interval. This could be solved by observing the star's position at shorter time intervals, which would result in a smoother curve. In fact, the distance traveled by the star between each time interval can be seen in the Desmos graph provided. Now, however, in order to estimate the black hole's mass, we could average all the data points. This was done, and in fact, the mass of the black hole was estimated to be 1.758 times 10 to the 34th kilograms. Thank you.